The great clockwork of the Allied strategic bombing campaign over Europe was a marvel of industrial might, logistics, and human endurance. It was an operation that tolerated death on a scale previously unimaginable, yet demanded an almost religious devotion to perfect maintenance. Every bolt, every wire, every hydraulic line on the four-engine giants, the B-17 Flying Fortress and the B-24 Liberator, had to be checked, certified, and cleared. Failure to do so meant death, not just for the 10-man crew of that aircraft, but potentially for the entire formation threatened by a mid-air collision. But within this system of almost sterile perfection, there were bound to be errors, small, human lapses, and it began, as so many great, dangerous mysteries do, with a tiny entry buried deep inside a maintenance log on a chilly afternoon in the late autumn of 1943. The location was RAF Thurleigh, Station 111, a sprawling, muddy base in Bedfordshire, England, home to the 306th Bomb Group, USAAF. The air was perpetually thick with the smell of high-octane fuel and exhaustion. The man in question was Technical Sergeant James Jimmy O'Connell, a flight line engineer, 24 years old, already possessed of the 1,000-yard stare of someone who had pulled too many shredded corpses out of returned aircraft. O'Connell was conducting a post-flight inspection of AB-17G, nicknamed the Dublin Daredevil, which had just returned, mercifully whole, from a punishing raid on an aircraft assembly plant in Oschersleben, Germany. His job was rote: check the control surfaces, look for flak damage, inspect the engine cowlings. But O'Connell had a particular specialty: engine cooling and pressurization systems. He was meticulous, tracing the complex plumbing that managed the pressure and temperature of the massive Wright R-1820 Cyclones. As he worked on the No. 3 engine, the starboard inner, he paused, his gloved hand resting on a crucial piece of hardware. It was a coupling leading into the engine's oil cooling system, a standard, robust piece of American brass and steel. But O'Connell's specialized pressure gauge, which he trusted more than the primary cockpit instruments, gave him a reading that made no sense. He filed a report that day, an obscure paragraph in the vast sea of technical jargon that flowed into the maintenance hangar. Observed pressure imbalance on R-1820 No. 3 oil cooler inlet. Initial reading 22 psi over spec. Corrected to 16 psi after idle test. Found coupling. Part number 77A109. Misaligned by approximate 1/32 of an inch. Tightened. Subsequent thermal spike noted at 1715. Unable to explain spike. Recommend deeper inspection. Nobody understood what he meant. The Dublin Daredevil had returned from Oschersleben without issues. The pilots had reported a flawless engine run. The airframe was intact. When O'Connell pointed out the supposed misaligned coupling to the shift supervisor, it looked perfectly snug. The unexpected thermal spike he recorded was a single, tiny peak on a long sheet of temperature graph paper, easily dismissed as a faulty sensor reading. O'Connell, his supervisor, Captain Hayes, had sighed, rubbing the sleep from his eyes. The engine is fine. The plane is flying. Leave the engineering to the factory boys. We have 22 ships flying tomorrow. O'Connell insisted, quietly, doggedly. Something is wrong, sir. Someone changed something. His superiors dismissed the claim as a technical misreading, the exhaustion of a young man under too much pressure, or simply a mistake, a single, insignificant glitch in the machine. They had no idea that this mistake would be the first tremor announcing one of the most insidious and dangerous hidden threats of the entire air war. Chapter 2. The Mathematics of the Missing. To understand the menace O'Connell stumbled upon, we must first understand the state of the air war in late 1943. This was the era of the unescorted deep penetration raid, often called the hard winter. The losses were brutal. The American air forces were punching deep into Germany, far beyond the range of their short-legged fighter escorts. The sky was a shooting gallery, and the bomber crews were sacrificial lambs. However, amidst the catastrophic destruction wrought by German Luftwaffe fighter squadrons and the dense walls of flak, there was a strange, creeping statistical anomaly. Allied bomber losses over Europe had been climbing for months, but not in the dramatic, single-day catastrophes like the infamous Black Thursday raid on Schweinfurt. Instead, the attrition was subtle, not catastrophic, not dramatic, just consistently, slightly higher than expected. The expected loss rate for a mission might be 4%. The actual rate hovered around 5.5%. Over months, this marginal difference translated into dozens of unexplained missing aircraft. More troubling were the reports of aircraft that suffered catastrophic, non-combat-related failures, engine fires, structural collapses, or uncontrollable spins, over German territory, far from enemy fighters or flak. These were dismissed as mechanical failure under extreme stress. Crews blamed the brutal, intense accuracy of new German flak gunners. Command blamed the unpredictable, deadly high-altitude weather over the continent. Intelligence blamed aggressive new Luftwaffe tactics, like the head-on assault or the Sturmbach heavy fighter groups. No one thought to examine the aircraft themselves, to look inward at the complex machinery that was supposed to be the crew's only sanctuary. The meticulous man, except for one man. His name was Flight Engineer Arthur Mallory, and he was O'Connell's direct commanding officer, the engineering sergeant major for the entire 306th Bomb Group. Mallory was the antithesis of the dashing pilot ace. He was a meticulous, stubborn perfectionist, a man built from patience and grease. He possessed a mechanical intuition bordering on the mystical, a man who believed that if a machine failed, it was always the fault of the human who built it, maintained it, or flew it, never the machine itself. He took every machine personally, viewing the squadron's fleet as an extension of his own responsibility. He had personally signed off on O'Connell's misalignment report, filing it away with a mental footnote. Jimmy is sharp, but tired. But Mallory was also the man who read every single report. He was drowning in data. Every pressure graph, every electrical flux report, every fuel consumption chart. He checked every weld, every stress fracture, every screw pattern on every returning B-17. He gave these bombers the kind of attention most men reserved for their own children. And he started seeing things the officers never noticed. The geometry of the impossible. Mallory wasn't looking for the obvious damage, the flak holes and cannon scars. He was looking for symmetry. Over the span of 6 weeks, 8 different B-17s had returned with nearly identical, small, technical defects. The planes were entirely different, flown by different crews, and had traveled on different missions. Yet the damage patterns were strangely, alarmingly consistent. Engine cooling inlet. A minuscule, almost microscopic burr on the inner lip of a high-pressure oil coupling. Always on the starboard engines, this tiny burr would cause a momentary flow turbulence, leading to the kind of pressure imbalance O'Connell had reported. Wing spar fastener. A specific rivet, always the 9th one from the root of the port outboard wing section, showed signs of being recently loosened and retightened, resulting in a microscopic area of fatigue around the rivet head. Fuel pump feed line. A specific brand of sealing washer used in the fuel pump feed line assembly was replaced, not with the high-specification factory standard, but with a nearly identical, but subtly weaker, commercial-grade washer. The patterns were too symmetrical, too consistent to be random flak damage, metal fatigue, or mechanic error. Flak was chaotic, fatigue was random. This looked like design. It looked as if someone had engineered the aircraft to fail at specific, calculated stress points. Mallory began to create his own diagram, mapping these points onto the B-17's blueprint. He traced the flight control lines, the engine systems, and the structural integrity points. What he found was chilling. These 3 points of micro-damage, taken individually, were insignificant. But in combination, they created a systemic weakness that would only manifest under the extreme, sustained stress of a combat sortie, high G turns, extreme altitude, and sustained heavy machine gun recoil. The effect would be delayed, gradual, and catastrophic. A high-pressure oil line could fail catastrophically under the combined stress of the turbulence caused by the burr and the high G turn. The weak rivet could shear, leading to structural flutter and wing failure. The inadequate washer could fail under pressure, leading to an insidious, low-grade fuel leak that pilots would mistake for high fuel consumption. Mallory had found the invisible clockwork of a slow-motion kill mechanism. The dismissal, when he reported his findings, meticulously documented with photographs and micron-level measurements, the officers did not congratulate him. They panicked, then scoffed. Colonel Harris, the base commander, listened to Mallory describe his geometric conspiracy of damage points. "Mallory, you're overthinking it," Harris said, gesturing vaguely at the mountain of paperwork on his desk. "We're seeing patterns in the stars. This is war. Parts fail. Mechanics make errors. This is statistical noise. A major from the USAAF's Technical Command, dispatched specifically to deal with Mallory's eccentric claims, was even more dismissive. "Sergeant," the major stated flatly, "your job is maintenance. You're trying to prove a conspiracy theory about bad washers. Leave the engineering to the engineers." The bitter irony was not lost on Mallory. He was the engineer. He was the one tracing the lines of stress and failure. And he wasn't wrong. He was looking at something so coldly professional, so deeply concealed within the operational flow of the Allied airbases, that it defied belief. A deep, well-placed cell of Axis-aligned saboteurs was methodically introducing slow-kill micro-defects into the American bomber fleet. They weren't blowing up planes on the ground. They were setting invisible time bombs, designed to detonate in the chaotic, high-stress environment of deep penetration raids, ensuring the German high command could write the losses off as mechanical failure. Mallory stood alone in the chill of the hangar, staring at the schematic of a B-17 that had just returned with its port wingtip nearly shot off. He knew the holes were from flak, but he now suspected the plane was only there to be shot at because the subtle damage he found had forced the pilot to fly a less efficient, more dangerous route. The invisible war had just begun, a war fought not with bullets and bombs, but with compromised materials and perfectly positioned imperfections. Mallory's fight was no longer against the visible enemy in the sky, but against a ghost inside his own hangar. Dismissed by his superiors, and facing thinly veiled threats of being shipped out of the relative safety of the maintenance hangar and into a frontline infantry replacement pool, Flight Engineer Arthur Mallory retreated into the solitude of his obsession. The official channels had failed him. The bureaucratic machine, designed to win the war, was now defending the very flaw that was killing its own men. He began working late at night, under the cover of the base's exhausted inactivity. Armed with a single, battered flashlight, a leather-bound notebook, and his engineer's intuition, Mallory became a ghost in the vast, cold hangars of RAF Thurleigh. He crawled through the grounded giants, the B-17s, paying attention to the parts the aircrew never saw and the parts the assembly line mechanics were paid to ignore. He was looking for the nexus, the single point where his disparate observations of a burr on the oil coupling, a weak rivet, and a bad washer converged. The common factor linking all his points of failure was sustained high-altitude operation under thermal stress. Everything about a B-17 mission, climbing to 25,000 feet, running the powerful engines at maximum manifold pressure, enduring temperatures that dropped to -50 degrees Celsius outside while the engine blocks churned at hundreds of degrees, was an exercise in mechanical extremism. The engine's heartbeat. Mallory focused his attention deep inside the engine nacelles, specifically on the fuel-to-air feed system of the massive Wright R-1820 Cyclones. This was a complex vascular network that ensured the proper mixture of fuel and oxygen was delivered to the massive piston assembly. Pilots rarely touched these parts. Mechanics inspected them for leaks, not composition. And that's when he found it, hidden behind a firewall and beneath a layer of protective cladding. It was a small, crucial component known as a fuel manifold valve body. Its job was to regulate the flow of high-pressure fuel just before it entered the carburetor. On paper, it was a perfectly ordinary piece of cast metal. But when Mallory compared the valve bodies from the returning, damaged bombers against the equivalent parts from the unlucky aircraft that had crashed during training, which used older, known parts, he saw the subtle, sickening difference. The old parts were stamped with the correct material code, alloy specification 44B, a hardened, stable nickel-chrome steel designed for minimal thermal expansion. The new parts, fitted to all the new production bombers, carried a slightly different batch number and, critically, were made of an alloy that Mallory recognized, a cheaper, commercial-grade aluminum zinc composite. The difference in cost was negligible in the grand scheme of the war, perhaps only a few shillings per unit. But the difference in performance was catastrophic. The cheaper alloy was perfectly stable at ground temperature. It was perfectly within tolerance for a brief flight, or a civilian airliner operating at 10,000 feet. But under the intense, sustained heat generated by the R-1820s operating for hours at peak thermal load deep over Germany, the metal began to expand. The microscopic assassination. The expansion was microscopic, a matter of a few 10,000ths of an inch or a few micrometers in modern terms. But in the precision mechanics of the fuel-air mixture system, this tiny expansion was enough to slightly distort the valve housing, minutely restricting the flow of high-octane fuel to the carburetor. The effect was insidious, subtle, and utterly deadly, fuel starvation at high altitude. The pilot wouldn't experience a violent explosion or a sudden seizure. Instead, he would feel a momentary, confusing engine sputter. A brief, unexpected loss of power, not catastrophic, but just enough to slow the aircraft. A slow, almost imperceptible drift out of formation as the other aircraft pulled ahead. This micro-sabotage turned the fully protected B-17 into a lame duck. Once a bomber fell out of the tight, defensively oriented combat box, it lost the overlapping protection of dozens of 50-caliber machine guns. It became an easy, isolated target for the waiting German fighters, which would converge for the kill. The plane would be shot down, and the subsequent crash and fire would destroy all evidence of the faulty valve body. The loss would be logged, shot down by enemy fighters. It wasn't a sudden, malicious act of sabotage like a time bomb. It was a cold, calculated engineering shortcut hidden inside a supply chain stretched to breaking point. It was a death sentence delivered by a pencil pusher worried about procurement costs. The confrontation, armed with his photographs, caliper readings, and a detailed theoretical analysis of thermal stress, Mallory confronted the visiting factory representative, a smooth, immaculately dressed civilian named Mr. Wallace, who was on a public relations tour to boost crew morale. Mallory cornered Wallace in his temporary office, spreading the documents across the man's polished wooden desk. "This part," Mallory said, stabbing a finger at the graph showing the thermal expansion curve, "is causing engine failure at altitude. It is failing under combat stress." Wallace looked at the graph with bored impatience. "Sergeant, I appreciate your diligence. But I have certified documents from the Directorate of Production and Materials right here," he tapped a folder, "that state those parts are perfectly within tolerance for military specification. Our quality control is unparalleled. Within tolerance at sea level and idle power, perhaps," Mallory retorted, his voice tight with controlled anger. "But not at 25,000 feet, running at 50 inches of manifold pressure for 3 hours. You are using an alloy that expands. It starves the fuel line." Wallace stood up, his voice dropping to a dangerous, icy whisper. "Sergeant Mallory, I am not a mechanic. I am a manager. And I am telling you bluntly, stop wasting our time. You have no combat experience. You are creating a panic over what is clearly an overstressed part that any mechanic would replace in a normal cycle. You are challenging the integrity of the entire supply chain. You will stop this investigation immediately, or I will ensure you face disciplinary action for insubordination." Mallory refused. He took the threat, pocketed his notes, and walked out. His refusal almost ruined him. The paperwork for his transfer and disciplinary review began its slow, cold churn. He had 3 days before the system purged him. He knew he had to prove his case, not to a manager, but to the pilots who depended on his work. Mallory knew that any official retesting would take weeks, and would likely be conducted on the ground, where the faulty component would perform flawlessly. He needed to prove the failure where it happened, 22,000 feet, under combat load thermal conditions. His mind began to work on a solution, a plan so reckless and utterly insubordinate that it should have earned him an immediate court-martial regardless of the outcome. He decided to stage the proof himself. He signed himself onto the manifest of the next morning's scheduled high-altitude test flight, a routine sortie to calibrate new oxygen systems, without the explicit authorization of his commanding officer. He used an old, unofficial signature stamp and filed the paperwork after midnight, ensuring it wouldn't be checked until after takeoff. He told the flight crew nothing. The pilot, a young man named Lieutenant David Harmon, simply assumed the chief engineer was hitching a ride to check the Dublin Daredevil's freshly serviced landing gear. At dawn, the B-17, loaded with nothing but fuel and a few test instruments, lumbered down the runway and climbed into the vast, freezing blue. The tunnel of fire. At 22,000 feet, the altitude where the internal engine temperature reaches peak thermal load, Lieutenant Harmon leveled off and announced over the intercom, "Engines running smooth." Starting the oxygen check, Mallory didn't answer. He had already crawled out of the safety of the main fuselage and into the cramped, terrifying engine bay tunnel, a narrow passage accessible only during flight, built primarily for emergency repairs or visual checks. The passage was directly adjacent to the wing spar and the 4 screaming, vibrating engines. He was wearing thick flight gear, but the noise was deafening, and the vibration was immense. He was in the belly of the machine, staring directly at the junction where the problem lay. He opened a small, circular inspection hatch that gave him a direct, albeit precarious, view of the number 3 engine's fuel manifold valve body. Mallory secured himself with a harness and waited, flashlight clamped in his teeth, his eyes glued to the alloy component. He watched for any sign of deformation, any shimmer of heat, or any irregularity. The plane bucked gently in the high-altitude turbulence. The temperature gauges in the cockpit showed the engines reaching their peak operational range. The thermal load was finally maxing out. And then, Mallory felt it. It wasn't a sudden, dramatic explosion. It was a subtle, violent change in the rhythm. The engine didn't fail. It went from a smooth, powerful roar to a sudden, sickening vibration, a deep, high-frequency shudder that resonated through the wing spar and into his chest. It was the mechanical equivalent of a heart skipping a beat, followed by an aggressive palpitation. This was it. This was the same vibration that had preceded the spin, the fire, the disintegration that had doomed so many bombers. The momentary flow restriction had caused a severe lean mixture, almost causing a detonation in the cylinder head. Mallory slammed his fist on the metal wall of the cockpit tunnel with desperate force, shouting the only command that mattered: cut throttle. Now, Lieutenant Harmon and his co-pilot, startled by the sudden, violent racket from the tunnel, reacted on instinct, hauling back on the throttles for the number 3 engine. The vibration stopped instantly. The engine noise smoothed out, dropping back to a healthy idle. Mallory had just proven the danger, and nearly died doing it. The microscopic expansion of the faulty valve body had been momentarily corrected by the reduction in engine temperature and pressure. But the most shocking part was not the confirmation of the fault. That was pure, predictable engineering. The shocking part, the part that elevated this from a simple story of industrial negligence to a dark, hidden chapter of the air war, was what happened next. As Mallory slowly, painfully, back into the main fuselage, bruised and shaking, the radio operator, Sergeant Miller, handed him a crumpled note, his eyes wide with fear. The note contained a single, chilling message, intercepted moments after the engine vibration began. Target acquired. Confirm termination. The transmission was brief, coded, and originating not from the ground, but from an aircraft somewhere in the blue above them, an aircraft that should never have been there. Mallory had not only exposed a systemic flaw, he had exposed the executioners waiting to exploit it. The air in the debriefing room was not heavy with victory or defeat, but with the cold, institutionalized dread of a massive failure of process. Flight engineer Arthur Mallory stood before a panel of officers, his face streaked with soot and exhaustion, the paper evidence of his unauthorized test flight spread out on the table like incriminating photographs. He was facing a potential court-martial for jeopardizing government property and disobeying direct orders. But the evidence he presented transcended military discipline. He had charts showing the sudden, violent pressure drop in the fuel manifold at 9:17 a.m. He had the thermal curves, which climbed to a critical peak, followed by a momentary, catastrophic stall just before the throttle was cut. The physics were undeniable. The part was failing, and it was failing in the exact thermal and pressure environment that every bomber encountered every single day over the target. Mallory also presented the intercepted radio message: target acquired. Confirm termination. This chilling detail elevated the problem from industrial negligence to something far darker. The micro defect wasn't just a flawed part, it was a beacon for opportunistic Luftwaffe pilots, or worse, a signal for a coordinated, low-effort attack. The subtle power loss was being tracked and exploited. The room, initially hostile, fell silent. Colonel Harris, who had once dismissed Mallory as a nervous eccentric, slowly picked up the graph tracing the engine's catastrophic vibration. He looked at the spike and then at Mallory. The weight of every missing bomber, every lost crewman logged as killed by enemy action, suddenly settled on the small, cheaply made alloy valve body. The truth was finally understood. The Germans were winning the air war, not just through aerial combat, but through a hidden, insidious flaw in the Allied supply chain that guaranteed high-altitude failure. The unseen emergency. The response from the USAAF's 8th Air Force High Command was swift, brutal, and utterly silent. This failure could not be publicly acknowledged. To admit that hundreds of airmen had been lost due to a faulty, mass-produced component would be a devastating blow to public confidence, crew morale, and the prestige of the entire strategic bombing campaign. A quiet emergency order was issued, coded and rushed through the highest levels of the U.S. War Department, bypassing dozens of bureaucratic layers. The order was simple, yet demanded an industrial mobilization effort nearly as complex as the invasion of Normandy itself. Replace every single fuel manifold valve body in the entire Allied bomber fleet. The logistics were staggering. Industrial conversion. Factories in Ohio and Michigan were switched overnight from mass-producing the faulty aluminum-zinc part back to the original, high-specification nickel-chrome steel alloy, Spec 44B. Production quotas were immediately tripled. Field mechanics mobilized. Field mechanics across every bomber base in Britain, North Africa, and Italy were pulled from regular duties and put on specialized, 20-hour shifts. They were given one non-negotiable task: locate and replace the designated component. The lifeline: transport aircraft, C-47s and specialized high-speed cargo planes, were immediately tasked with nothing but ferrying the replacement parts, labeled with the highest possible priority code, to every bomber base in the European Theater of Operations (ETO). The operation was executed with a silent, desperate efficiency that mirrored the urgency of a field hospital triage. To maintain operational secrecy and prevent a devastating collapse of morale, the pilots were never told the full story. As far as the aircrews knew, the frantic activity in the hangars was just another routine maintenance update, or a necessary winterization protocol required for engine longevity. The new parts were slipped into the aircraft in the dead of night, replacing the flawed component that had been a tiny, ticking death clock in their engines. Only the highest echelons of the engineering corps and the handful of men who worked the long, cold nights in the hangars, men like Mallory and O'Connell, truly realized the catastrophe that had been averted. They had witnessed the systematic dismantling of a hidden, industrial-scale act of slow-motion mass murder. Chapter 6. The Silent Proof. The immediate aftermath of the replacement operation saw no fanfare, no public announcement, and no change in the official loss statistics, which were retrospectively analyzed much later. The war marched on, brutal and exhausting. But when the next major bombing campaign launched 2 weeks later, a massive series of raids against the German heartland that would typically cost the Allies a staggering number of heavy aircraft, the analysts and commanders noticed something strange. Something that defied all statistical prediction. The expected losses didn't happen. The American bomber groups were still battered by flak and engaged by furious Luftwaffe fighters, but the attrition rate from non-combat causes vanished. Formation integrity. Bomber groups held formation longer and tighter. There were fewer reports of aircraft slipping out of the protective combat box due to power management issues. Engine performance. Engines performed flawlessly at maximum thermal load and altitude. The pilots, relieved of the nagging, subtle fear of a sudden sputter, could push their aircraft harder, maneuvering more effectively to avoid flak and close with their neighbors for defensive fire. The lame ducks disappear. German fighter pilots, according to later captured documentation, began reporting a frustrating lack of stragglers, the isolated, easily targeted bombers that had been their bread and butter. The sudden, systemic failure that had provided the Luftwaffe with its easiest kills had evaporated. The casualties dropped sharply, not to zero, but enough that the 5.5% loss rate normalized back down to the expected 3.5–4.0% loss rate for deep penetration. That 1.5% margin, sustained across thousands of sorties, represented a colossal, immediate saving of life and materiel. Historians, analyzing the data decades later, were finally able to quantify the impact of Mallory's discovery. Conservative estimates suggest that over the remaining months of the war, the timely replacement of the faulty valve bodies saved over 3,000 Allied airmen, men who survived the war specifically because one man refused to ignore his mistake. The unsung hero, Arthur Mallory, never became famous. His original report, the one that had been mocked and dismissed by his superiors, had contained a single, awkward, technically correct sentence that exposed the entire conspiracy of negligence, pressure differential inconsistent with design specs, possibly due to manufacturing variance. That one sentence, the fruit of his obsessive, flashlight-fueled investigation, forced an industrial redesign that saved entire bomber groups. Mallory never received medals for his actions. The official record of the unauthorized test flight was quietly expunged, replaced with a commendation for outstanding diligence in routine maintenance procedures. The true, dark reason for the massive replacement campaign was locked away in classified archives, where it would remain for generations, deemed too sensitive for public consumption. He never saw combat. He retired from service immediately after the war, disappearing back into the anonymity of civilian life. Most of the thousands of pilots he saved never learned his name. They returned home, raised families, built businesses, and lived the lives that had been snatched back from the statistical shadow of a corporate error. Yet, thousands of Allied families owe their future, the very existence of their next generations, to one stubborn flight engineer, the man who was told to leave the technical work to others, and the mistake that exposed a hidden flaw before it destroyed them all. He won his war not with guns or glory, but with a caliper, a flashlight, and the unshakable belief that a machine should be, above all else, honest.